In this video, we will present the programmable devices. Three types of combinational programmable logic devices, and they differ in the placement of the programmable connections in the AND or array. The most flexible one among these is called PLA or Programmable Logic Array, which we will focus more in this video. This is because both the AND array and the OR array are both programmables. The product terms in the AND array may be shared by any OR gate to provide required sum of products implementation. To explain further, the read-only memory that is presented in a different video, which is programmable. It's called a programmable read-only memory. It has fixed AND array, which means it has a complete decoder n by 2 to the power n, whereas the OR array is a programmable so that we can take the minterms that we want. Contrary to this exactly is what is called a programmable array logic, PAL, which has a fixed OR array, but the AND array is a programmable. And as we have just mentioned, the most flexible is the PLA, which is a programmable logic array, where both the AND array and the OR arrays are both programmable. Let us more look at the programmable logic array, because this is what we will use in this video. The PLA is similar to the PROM, except the PLA does not provide full decoding of the variables. In other words, we don't have a decoder as it is in the ROM. We don't have this. We program the AND gates, and the decoder is replaced by an array of AND gates, and these can be programmed to generate any product term that we need. And each input variable is made available in normal and complemented form. So if we have variable x, it's a variable x and x prime, y, y prime, etc., by using a buffer inverter combination, as we will see next. So an example on the PLA, which we use to implement the functions, two functions, f1 equals ab prime plus ac plus a prime bc prime, and f2 equals ac or bc prime. And as we said, each variable is available. We have three variables here, a and b and c. So we pass a into this circuit here, which provides both a true value of a and complemented value of a. So this is available a and a prime. Same thing, we have available b and b prime and c prime. Now we program the PLA in order to obtain the products that we have here. So we have here AB prime, AC, A prime, BC prime, and BC. So we program it to provide 4 products. The product terms are programmed like this. We make as input to this AND gate, we put a cross here, so we connect it to here and to here. So it's connected with A and B prime. So this is AB prime. And the other one, A and C, so it's connected with A and C. The third one, B and C, we connect it with B and C. And the last one, A prime, BC prime, so we connect with A prime and B and C prime. And then the product terms are then connected to OR gates to provide the sum of products for the required Boolean functions. So this now we have 4 products, these ones, A, B prime, A, C, B, C, and A prime, B, C prime, and we want F1 to be the ORing of the first these 3. So we have an OR gate for F1, which is this one, and with this OR gate, we connect it with AB prime. We look here, so we take this one, and then AC, so we connect it with AC, and we connect it with A prime, BC prime. So with this one, and this would be the output to produce F1. Same thing exactly for F2. We connect AC and BC. So this is the programming of the OR gates. We explained it, and before that we explained the programming of the AND gates. Now the final stage is using an exclusive OR array also. So the output of the OR gate goes to an exclusive OR gate where the other input can be either 0 or 1. We know from before that exclusive OR of x and 0, we get x, and if we exclusive OR x and 1, we get x prime. So we bring this output here to another gate, exclusive OR gate, and we want F1 to be the ORing of these. So the other input of the exclusive OR will be logic 0. And for F2, we bring this output of the OR gate here, and the other input will be logic 1, so we connect it with 1, and this is F1, and this is F2. So this is how we can program, as we said, both the AND gates, the OR gates, and the exclusive OR gates in order to implement the function with the PLA. Let's take another example. Well, let's explain more before the other example. The construction of the PLA, it is done actually through what we call PLA programmable map. Now, there's a fuse at every interconnection, and the fuse map, we call it, of the PLA is specified in tabular form and programming table, we call it. The product terms are arranged alphabetically, so we have AB prime, that's the first one, and then AC, and then BC, and then A prime, BC prime. And then we have the inputs ABC. For AB prime, we put 1 here and 0 here and dash here because this product is A is true and B is false and T does not appear. Same thing for A and C. We put 1 here and nothing under B. And the third one, BC, we put dash 1, 1. And the last one, A prime, BC prime, 0, 1, 1. So this is the programming of the AND gates here. And then the programming of the OR gates, it is in order to implement F1 and F2. So F1, we put 1 here for this product. It is included in F1, and 1 for the AC, and nothing because we don't take BC, and 1 for the last product. And for F2, we put 1 corresponding to AC and 1 corresponding to BC, and this is the part of the table that programs the OR gates. Finally, we want to program the exclusive OR gates, and this is done by putting true or complement here. A true means F1 is equal to this summation as is, and complement means F2 equals this summation complemented, which means we program this by putting 1 input to the exclusive OR gate. Let us take another example now to make sure it's clear. Example, it is normal Boolean function implementation, and it is asking us to implement 2 Boolean functions with a PLA. The first one, F1 equals sigma 0124, F2 sigma 0567, and each of function is function of 3 variables A, B, and C. So we construct 2 kernel maps, one for F1 and the other for F2, and F1 will contain min terms M0, M1, M2, and M4 here, and the other one M0 and M5, M6, M7. Now, the 2 functions are simplified using the kernel maps, and in order to get the best PLA implementation, we have to find out both the true value of the function and the complement of each function in order to see what is best in order to implement the function. Now for this one, look, if we take the ones, F1 will be this loop, and this loop, and this loop. This is in the true form, and in the complemented form, F1 equals this loop plus this loop plus this loop complemented. And for F2, we have the true form, we have this min term, and this loop, and this loop. That's in the true form. In the complemented form, we have this loop, or this loop, or this cell, all complemented. And we can see next the expressions that we find. We find from the previous kernel maps, this is the expression for F1. It has the 3 products that we can see here. And for F1 in complemented form, this will be the expression. Please verify this at your time. You need to make sure that you understand this correctly. And for F2, This is the true expression, and this is the complementary expression. Then we need one more exercise, as a matter of fact, which is the following. Now, we can take either the true value of F1 with the true value of F2, or a true value of F1 with F2 complemented, or F1 complemented and F2 true, or F1 complemented and F2 complemented. To make it easy for you, we have summarized this in this table here, where F1 is either true or false or complement, and F2 is either true or false, which is complement. So we can say this complement if it is more suitable to you. Actually, it makes no difference, but this is not C, it is the complement. And we write here the product terms in each solution. And in the first case, if we take this expression for F1 with this for F2, we get six product terms, which are shown here. Whereas if we take this one for F1 and F2 complemented, we have also six products, which we can see here. And then if we take F1 complemented with F2 true, we have 4 products that we can see here. And finally, if we take F1 complemented and F2 complemented, we have 6 products that we can see here. Which combinations out of these 4 gives us the minimum number of product terms? We find it this one. So we take then F1 equals AB plus AC plus BC prime complemented, and F2 equals AB plus AC plus A prime, B prime, C prime. So we have only 4 products that we need to implement in the PLA. Then comes as follows, the programming table. We have 4 product terms, which are here: AB, AC, BC, and A prime, B prime, C prime. And the first one, programming the AND gate, we put under the inputs A1 and B1 and C nothing dash, AC1 dash 1, BC dash 1 1, and the last one 0 0 0. And this is again programming of the AND array here. To program the OR array, now we take F1 equals AB or AC or BC. So we put 1 1 1 dash, because we don't take this one in F1. And same thing for F2, we put 1 corresponding to AB, 1 corresponding to AC, and 1 corresponding to A prime, B prime, C prime, and nothing under BC. So this is the programming of the OR array. Finally, we need to program the exclusive OR array. F1 is obtained by complementing these products when OR together. So we put complement here, so that the exclusive OR will get input, the other input will be 1, and F2 will be the true value of this. So this explains in detail how we can use PLA in order to construct